Okay, we have begun to look at the symmetry operations as matrices. And why can we do this? We can do this because we can express the coordinates of an object as a matrix. So when a symmetry operation transforms an object, then it transforms it from old coordinates that can be expressed via a matrix to new coordinates. So for that reason, any matrix that, when multiplied with the matrix representing the old coordinates of the object, and produces correctly the new coordinates of the object, can be considered a mathematical description of the matrix, a matrix description of the matrix. Sorry, a matrix description of the symmetry operation. So we have illustrated this concept for one example already. So we looked at the water molecule, which belongs to the point group C2V, and we have seen how the C2 symmetry operation transforms these coordinates. That we have seen that the coordinate x transforms into minus x, the coordinate y transforms into minus y, and the coordinate z transforms into minus z. And that the matrix that, when multiplied with the matrix for the old coordinate, gives the new coordinates has this form here. It's -1, 0, 0, 0, -1, 0, and 0, 0, 1. So now we can do the same procedure also with the other symmetry operations in the point group C2V. So the water molecule does not only have a C2 symmetry operation associated with it, but also two mirror planes. So the first mirror plane is the one that stands within the xz plane. So this is, in this case, the plane of the molecule. So let's see how the coordinates are being transformed in this case. So what will happen to x? Maybe anyone, can you say this, or I do the first part? Okay, so if we have the mirror plane being in the xz plane, then nothing will happen to the coordinate x, right? And the same is true for the coordinate z. So the coordinate z is also part of the plane, therefore the coordinate z will remain unchanged. However, the coordinate y, what will happen to the coordinate y? Will it be changed as well, or will it not be changed as well, or will it be changed? Yeah. Yeah, it should be mirrored. So that means that it will change. Okay. So the vector that will point to the coordinate y in the object will actually reverse its sign. Okay. Point into the other direction. And therefore, y will be transformed into -y. All right, so we know in this case that the new coordinates here, x prime, y prime, z prime, will be x minus y and z. Okay, so now again, we need to find the matrix that, when multiplied with the original coordinate, gives correctly the new coordinates. Okay, so in this case, this is this matrix here, 1, 0, 0, 0, -1, 0, and 0, 0, 1. You could again apply the multiplication rules for matrices in order that this is true. Maybe we can just do this one more time as an exercise. So if we multiply the first row with this column, that means that we have 1 times x plus 0 times y plus 0 times z. Well, that gives just x, right? So then we have 0 times x plus minus 1 times y plus 1 times z. Well, that gives minus z. And last but not least, we have 0 times x plus 0 times y plus 1 times z, and that gives us correctly z. So now we have found also the transformation matrix for sigma x. So next we can look at sigma yz. So sigma yz is this sigma prime mirror plane. Then in the yz plane, which bisects the molecule. So this is the mirror plane that actually swaps up the 2 hydrogen atoms. Okay, so now how do the coordinates change in this case? Let's start with the coordinate x. What will happen to the coordinate x? Can anybody tell me what happens to the coordinate x? Okay, stays the same. That is actually not true, okay, because our mirror plane here is in the YZ plane. Okay, if we mirror the x coordinate at the YZ mirror plane, it actually changes its algebraic sign. It will flip around and point into the other direction. Okay, so now what about y? Will y change? Or will it stay the same? It remains the same, correct? Because the y-axis is part of the y-z plane. It stays the same, and for the same reason, the z coordinate also stays the same. Okay. So this means that y and z just stay what they are, but x changes its direction. You can also say the x coordinate changed its algebraic sign. So this will mean that our new coordinates x prime, y prime, z prime will be minus x, y, and z. So now what will the transformation matrix be? Well, in this case, the transformation matrix multiplied with the old coordinates x, y, and z. Well, that's this. And we'll have the form minus 1, 0, 0, 0, 1, 0, 0, 0, 1. You can apply. Oh, there's a question. So depending on what plane it is in, it will be whatever one isn't in the plane we are looking at that changes. Yeah, it is coordinate. It's the coordinate that is not in the plane that will change. That's correct. Yes. Okay. So we have here -1 times x plus 0 times y plus 0 times z. Well, that gives minus x. 0 times y plus 1 times y plus 0 times z. Well, that gives y. And 0 times x plus 0 times y plus 1 times z. Well, that gives z. So again, multiplication rule for matrices, we can show that this is the correct transformation matrix. So what other symmetry operation is still left? Well, there's of course still the identity. The identity is trivial, but nonetheless it's there. So therefore there should also be a transformation matrix associated with the identity. So now the identity never does anything with an object. So therefore, of course, all the three coordinates will remain the same. And the transformation matrix will have the form 1, 0, 0, 0, 1, 0, 0, 0, 1. Because this matrix multiplied with the old coordinate gives the new coordinates, which are the same as the old coordinates. Okay? So we can show this again by doing the quick calculation. So 1 times x plus 0 times y plus 0 times z. Well, that gives just x. 0 times x plus 1 times y plus 0 times z. Well, that gives just z. Sorry, y. And 0 times x plus 0 times y plus 1 times z. Well, that gives just z. So now we have found all the transformation matrices for all the symmetry operations that are in this molecules and that are in the point group C2V. Okay. So now you see here in sum the four matrices. So what do these matrices have in common? Well, first of all, you see that they all have in common that they have non-zero values only here on these diagonals on the matrices. And these diagonals have a special name. In mathematics, they're called the trace of the matrix. So now, what would the numbers on the trace of the matrix mean for each line? Well, the numbers here in the first row, 1, -1, -1, and 1, would basically tell you what the symmetry operations would do with the x-coordinate. Okay, 1 would mean, well, the x-coordinate doesn't change. As we carry out the C2 symmetry, as we carry out the identity, it would reverse sign as we carry out the C2. It would also reverse sign when we carry out the sigma yz. But it will not change its sign as we carry out the sigma x. Okay, so if we write these four characters here on a line, okay, then this line of characters would have exactly that meaning, would tell us what the symmetry operations do with the x-coordinate. So these characters, basically written in a row, are called an irreducible representation. And one number in an irreducible representation would be called a character within the irreducible representation. So this would be the irreducible representation for the x-coordinate. We could also define irreducible representations for the y and the z-coordinate respectively. So the irreducible representation for the y-coordinate would be represented by these four characters here: 1, -1, 1, and -1. You see the same numbers here again: 1, -1, 1, and -1. And the irreducible representation for the z coordinate, well, would be made of these four numbers: 1, 1, 1, and 1. Okay, you see this again here: 1, 1, 1, and 1. So now one can add irreducible representations, and the result of that is then in mathematics in group theory called a reducible representation. So if we add up actually all three irreducible representations, then this gives a so-called reducible representation that would have the characters 3, -1, 1, and 1. Okay, now an irreducible representation in group theory is associated with a certain symmetry type, and the symbols you can see here, that is defined by the characters in the respective irreducible representation. So for instance, the irreducible representation for the x coordinate is of B1 symmetry type, that for the y coordinate is of B2 symmetry type, and the one for the z coordinate is of A1 symmetry type. So what do these letters and subscripts actually exactly mean? So B means actually antisymmetric with regard to rotation about the principal axis. Okay, so the principal axis is in this case the C2 axis, and you see here that both for the x coordinate and the y coordinate, the characters underneath the C2 are -1. So for that reason, the irreducible representations associated with the x and the y coordinate are of B type. So the subscript 1 means that the representation is symmetric to a C2 perpendicular to the principal axis, or if lacking, to a vertical mirror plane. So in this case, we do not have a C2 perpendicular to the principal axis, but we have vertical mirror planes. Okay, and if we have several ones that are non-conjugate, we always look at the one with the smallest number of primes, which would be in this case the sigma v. So now that means that the coordinate x is of B1 type, because we find here the character 1 underneath sigma v, and the coordinate z also has a subscript 1, because the sigma v operation is associated with the character of +1. Okay, so the character of +1 means symmetric. So, well, when there's subscript 2, then the representation is antisymmetric, and that means that the character in the irreducible representation is -1. Okay, you see this here. So for that reason, the irreducible representation associated with the y-axis is of B2 type. It explains the subscript 2 here. All right, then we have not explained what this A means. Well, this A means just that we have a situation which is symmetric with regard to rotation of the principal axis. Remember, B means antisymmetric. Antisymmetric means where the character in the irreducible representation is -1, and the character is +1, then we have a symmetric situation. For that reason, the irreducible representation associated with the z-axis is of A1 type. Okay. Now the group theory is more powerful than just being able to say, well, which coordinate has which symmetry type. It is more general. It can actually say what is the symmetry type of a mathematical function in a particular point group. Now remember, orbitals are wave functions and can be expressed as wave functions. So for that reason, group theory is also able to predict what is the symmetry type of a particular orbital in a particular point group. In the next step, we will apply what we have learned just before, irreducible representations to orbitals. Okay, so let us stick with our water molecule. Okay, and let's put ourselves on the oxygen atom. And let's think about what the 2s orbital in the oxygen atom within the water molecule, what symmetry type does it have? So we can do this by inspection. We can determine what the symmetry operations do with our 2s orbital. And if the symmetry operations do not do anything with this orbital, then it gets the character 1. And if there change in the algebraic sign of the wave function, then it gets a character of -1. So now in this case, whatever symmetry operation we apply, our 2s orbital will remain unchanged. So for that reason, for each symmetry operation, the character would be +1. And that's only the case for the irreducible representation of the type A1. We therefore can say that, well, this orbital within the point group has a symmetry type of A1. Okay, now let us do this with another orbital, the 2pz orbital of the oxygen atom. Sorry, I'm still coughing a bit. So now, as we apply the identity, well, we would not expect that this orbital changes in any way. If we apply the C2 symmetry operation, we rotate around the z-axis, which stands here. We realize, well, nothing changes in the orbital. Now, as we apply the sigma v operation, we see, well, also nothing changes. And as we apply the sigma yz, we see, well, our orbital also remains unchanged. So again, that means that our 2pz orbital in the point group C2v must have the symmetry type A1. So now let's go from the 2pz orbital to the 2px orbital. So will the identity change anything? The answer is, well, the identity never changes anything. Will the C2 change anything now? And the answer is yes. Because as we carry out symmetry operation, the, well, left lobe of the orbital will move to the right, and the right one will move to the left, and the algebraic sign of the wave function changes. Okay, this is indicated here by a color change. Okay, but remember, color change stands for the algebraic sign for the wave function. So orange we have previously defined as positive, and blue we have defined as negative. So we can therefore say that, well, as we carry out the symmetry operation, our wave function changes its algebraic sign. And for that reason, we would now associate a character of -1 for that symmetry operation. So that means that our 2px orbital cannot be A-type, it must be B-type. It can either be B1 or B2. So whether we have B1 or B2 now depends on, well, what will the symmetry operation do when the sigma v mirror plane is being applied? Okay, so the sigma v mirror plane stands within the plane of the molecule. So as it stands within the plane of the molecule, does the algebraic sign of the wave function change or not? Yeah, we have an answer. No, it does not change. Correct, Alison, it does not change, and therefore the symmetry type must be B1. Okay. So we could have also asked, well, what is the sigma yz plane doing? Okay. Now the sigma y yz plane stands perpendicular to the molecule. So in this case, it actually would again change the algebraic sign of the wave function. So that is again consistent with the symmetry type B1, because you see here that for the symmetry type B1 underneath sigma v prime, you have the character -1. So now let's go from the 2px to the 2py. So the 2py orbital stands perpendicular to the paper plane. So one lobe points out of the paper plane and the other lobe points into the paper plane. So you see that in this case, the orange lobe points to the front and the blue lobe points to the back. So now in this case, what is the symmetry type? Well, the identity does nothing. What does the C2 symmetry operation do? Will it change the algebraic sign of the wave function or not? Yes, it will change the wave function. Yeah, it will change its algebraic sign. That's right. Okay, so the blue lobe will point to the front after carrying out the symmetry operation, and the orange lobe will point to the back. So therefore, again, we would expect the B-type symmetry type. Now, is it B1 or B2? We can decide this when we go to the next symmetry element. Sorry about that. The sigma V mirror plane. So as we carry out this sigma V symmetry operation, which is a reflection at the XZ plane, will our algebraic sign change or not? It will change, yes, correct. So for that reason, we must have the B2 symmetry type, where that character here is -1. So we can also check for the last symmetry operation, the sigma V prime, which is the YZ plane. So as we reflect at the YZ plane, which actually stands here, will the algebraic sign change? No, that's correct. So that confirms that the symmetry operation is B2. Okay. So now the properties of the orbitals could have also been predicted in somewhat a different way. Okay. And that works the following. Remember when we discussed atomic orbitals, we learned that a 2px orbital is a linear function of x. Okay, and that was the angular part of the wave function. And we saw that, well, the angular part of the wave function is only a linear function of x. Okay. So now as an x coordinate has a symmetry type of B1, any mathematical function which is a linear function of x has also that symmetry type. For that reason, the 2px orbital must have that symmetry type. So we termed it previously by inspection to see how the wave function changes. Now, another way to predict that would be, well, to remember that the 2px is a linear function of x, and because it's a linear function of x, it must be B1. So remember, the 2py orbit is a linear function of y, and that is again is the angular part of the wave function here. And for that reason, it must be B2. Now, the 2pz orbital is a linear function of z, which explains why it's A1. And the 2s orbital has no coordinate in its angular part of the wave function. So generally, any function which are not a function of a coordinate, they always have the symmetry type which is totally symmetric. That means the symmetry type in which all characters in the irreducible representation is 1. In our case, in the point group C2V, that's the symmetry type A1. See, all characters within that line here are +1. All right. So now we can extend these considerations also to d orbitals. So the oxygen molecule and the water molecule also has d orbitals. They are not occupied, but nonetheless they are possible states, and we can determine what are the symmetry types of these. So we can start with the dz square. Can anybody tell me what is the symmetry type of the dz square? So in order to determine this, just ask, what do the individual symmetry operations do with this wave function? Does the algebraic sign get changed or not? If it's getting changed, the character is -1. It's not getting changed, the character is +1. And that will lead you to the identification of the symmetry type. A1, that's correct. So none of the 4 symmetry operations do anything with this orbital here. Therefore, symmetry type is A1. That's correct. So now what about this one here? So this is actually the BXZ. All right. B1. Yeah, I think this is correct. B1, why is it B1? Well, the C2 axis will actually flip the wave function, as it will move this blue lobe here to the right and this orange lobe here to the left, and this orange lobe here to the right and this blue lobe here to the left. And in addition to that, the sigma v will not change the algebraic sign. So that means it must be B1 and not B2. So now what about this one here? So this is actually the d x square minus y square. Would it be A1? Yes, I think this is correct. Yeah. So again, none of these 4 operations do change the algebraic sign of the wave function. What about this orbital here? So this is actually the dyz. Okay. B2, yes, that's correct. B2. Why is it B2? Well, again, as you see, 2 actually changes the algebraic sign. It moves this blue lobe here to the front and this orange lobe here to the back, and that blue lobe here to the back and this orange one here to the front. Now, on the other hand, the sigma v mirror plane here in the plane of the molecule also changes the algebraic sign. And it does the same. It moves this blue lobe here to the front, this orange lobe to the back, this blue lobe here to the front, this blue lobe here to the back, and this orange lobe in the back to the front. Okay, so last but not least, we have here the dxy. So what is the symmetry type of that? And maybe I can answer this question. This one has the symmetry type A2, okay? And this is a symmetry type we have not considered before. That is because none of the coordinates x, y, and z have that symmetry type, okay? Now, the dx 3dxy orbital not necessarily needs to belong to one of the 3 symmetry types that we have encountered, because it's not a linear function of x, of y, or of z. Therefore, it can also belong to something else, another symmetry type that we have not considered yet, and that's symmetry type A2. Okay, so the symmetry type A2 is associated with these characters here. So of the identity, we have +1. For the 2, we have +1. For sigma xz, we have -1. And for sigma yz, we also have -1. We can verify this when we rotate around C2. Okay, we move this blue lobe into that position, and this blue lobe into that position, and this orange lobe into this position, where there is the other orange lobe and the back orange lobe here to the front. So overall, our wave function will not change its algebraic sign. So it has to be A-type, but it's not A1, but A2, because as we reflect, the algebraic sign changes. So as we reflect as the mirror plane, which is in the plane of the molecule, the algebraic sign changes because these 2 here are being swapped up, and these 2 here are being swapped up. But also as we reflect at sigma v prime, the algebraic sign changes. In this case, these two here are getting swapped up, and these two here are also getting swapped up. All right, so that's consistent with A2. So now, how many symmetry types can there be for a particular point group? There can only be a finite number of symmetry types. In the point group C2V, it's actually these four, okay? So any mathematical function must belong to one of these four symmetry types, these four irreducible representations within that point group. So now a full set of irreducible representations defines a character table. Defines a character table, and maybe we can do this as the very last point in this class. A character table is basically a table of rows and columns for a particular point group, and it tells us which mathematical functions have which symmetry type. So you see here a complete character table for the point group C2V. So you see here in the left upper corner, the point group symbol for the point group. Okay, and then right to that, you see here the different symmetry operations in different columns, also called classes, which are non-conjugate. Okay, so symmetry operations that are conjugate are grouped in the same column. Symmetry operations that are not conjugate, they are grouped into different columns. So for instance, the two mirror planes in the water molecule, they are not conjugate. They are distinguished by primes, and therefore they're getting different columns. If they were conjugate, they would be in the same column. Okay, so then here to the right, you actually see a column for the linear function. And here to the very right, you see actually a column for mathematical square functions. So these functions are being listed in the rows that represent the different irreducible representations. So for instance, Z stands here in the row, well, representing the irreducible representation of the symmetry A1, because any linear function of Z is having that symmetry type. Okay, so the Y coordinate, for instance, here stands in the row for the symmetry type B2, because the Y coordinate, as well as any linear function of Y, has that symmetry type. So here you see actually another column for square functions. So for instance, you see x squared, y squared, and z squared listed here in the first row for the symmetry type A1. That means that any linear function of x squared, y squared, or z squared has that symmetry type. Okay, so I see that our time is over, and I will complete the description of the character table the next class, so this was